Okay, let's start now with the definition of converge. The sequence AN converges to the real number A if the following is true. If for every epsilon greater than 0, so every little tiny positive number that you can give me, there is a capital N in the natural numbers, it's an index, such that for all of the indexes greater than or equal to that capital N, if N is greater than or equal to capital N, then the distance between AN and the limit is less than epsilon. Remember what this is. The distance between the term and A. For all values of N greater than that capital N. All right, that's the definition. So maybe I'll warm us up a little bit because we're going to be doing a lot of proofs proving that sequences converge. So the proof, if we have a sequence given to us, it won't be AN, it'll be AN is equal to something. We'll have to say, first of all, give me an arbitrarily chosen epsilon. So you'll say, let epsilon greater than 0 be given. And then what our job is to prove that limit exists, that it's a convergent sequence converging to A, we have to find this capital N. And then prove that as long as N is bigger than that, then this difference, this distance, is less than epsilon. Let's look at an example that we've already seen. Let's do AN equals 1 over N. We've seen this one already. And by the way, if ever I fail to write this N as an element of the natural numbers, or N equals 1 to infinity, it's implied. I may accidentally leave it out, or maybe on purpose if I'm in a hurry. Okay, we know that this is the sequence 1, 1/2, 1/3, 1/4, and so on. That converges to 0. I'm not going to write out the formal proof, but I'm going to explain why. Basically, this is always a positive number, and it's shrinking down to 0. It's never going to hit 0 because 0 is not an element in this sequence. But you can get it as close to 0 as you want. So for example, and again, this is not the proof, but if we choose an epsilon to be equal to 1 over 100, then for capital N equals 101, we see, or we have, the following. N greater than or equal to capital N implies the distance between AN and 0. Well, let's do some arithmetic on this. That's just equal to this. And that's just equal to this. And that is less than or equal to that. Hopefully you agree with that. N is at least as large as capital N. It's a minimum of capital N. And we chose this to be 1 over 101. So we've just shown the moral of this story is that this is less than 101. Whenever N is greater than or equal to capital N. So suppose I chose epsilon equals even a smaller number, 1 over 1,000. Well, we should be able to figure out fairly simply that if epsilon were 1 over 1,000, I would have chosen N equals 1,001. So it's important to note that the choice of epsilon the choice of capital N may depend heavily on the choice of epsilon. All right, I'm going to squeeze in an alternate definition here. Alternate definition. Really, it just means I'm using symbols instead of writing it out as a sentence. Okay, and here this is important. This is my shorthand for saying that the sequence an, and I left off the n equals 1 to infinity, and I will frequently do that in this shorthand. As a matter of fact, I might even leave off the squiggly brackets and just say an arrow, capital A. This means that an converges to the real number a if, I don't want to get too crowded over there, if for every epsilon greater than 0, there exists a capital N in the natural numbers such that the following is true. One more line. All I'm really going to do is write this thing a little bit differently right here. If the distance between an and its limit is less than epsilon, that means that an is in between a plus epsilon and a minus epsilon. And then I need to say, since I didn't say, since I didn't say little n is greater than or equal to n, I need to say it now. So I'll say whenever n is greater than or equal to capital N. So it's exactly the same definition, just written in a different way.